Good morning. At University of Auvergne, France, and today I will be presenting my work on 3D reconstruction of deformable objects. Shape-from-motion is a generic term for a set of methods that recover 3D shape from 2D images. In terms of rigid objects, we have multiple views of an object, and therefore we have too many constraints, and this kinds of things are very solvable, and we have very stable solutions for these. When it comes to non-rigid objects, this situation becomes very complex because when we have multiple images of the objects, the shape of the object in each image is different, and the goal is to recover n different shapes from n different images. So there are a set of methods which perform non-rigid reconstruction, and they assume that the object undergoes isometric deformations. These are the kinds of deformations where the 2 points on the surface, the geodesic distance between these points doesn't change when the object is undergoing deformation. A good example of such objects are for like a piece of paper or a piece of cloth. Isometric deformations are good to study because most of the objects in nature, they undergo similar to isometric deformations. So let's look at our method, isometric NRSFM in linear time. Our method assumes a calibrated perspective camera. We give a point-wise solution so we don't have to deal with occlusions and missing data. Our system solves two quadratic equations for each pair of views, and this has only two variables. So we have two equations, two variables, so we can solve it for two images, but then we need three images to disambiguate the solutions. Further in the presentation, we will see that we have actually two variables for n number of images, and this means that we have linear complexity in number of views. This is the basic mathematical model of our problem. So we have m1 to mn, n surfaces of the object undergoing deformation, and then we have I1 to In, n corresponding images. We have eta 1, 2 and eta 2 to 1. These are the registration warps between the images. These are computed using the point correspondences on the images. Phi is the embedding function. It's a 2D to 3D function from image to the surface. This is a very important function for our formulation because if we know phi, we know everything about the surface. So our goal is to find phi. Psi is the deformation function. We do not is undergoing isometric deformation. We have these are the following sets of knowns and unknowns. We know everything between the images, but in the surfaces, and our goal is to find that. We borrowed two concepts from Riemannian geometry. The first is metric tensor. Metric tensor is used to calculate areas and distances on the surfaces. It represents a differential area around a point, and we can see that we can write the metric tensor in terms of the Jacobian of the embedding is Christoffel symbols. These are the be written in terms of the metric tensor. Now, since we have two surfaces, Christoffel symbols on these surfaces, and since write the metric tensor and the metric tensor and Christoffel symbols on the we can, and this is the reason why we have a limited number of variables for assumption that we make. We assume that in the surfaces are planar. The Christoffel symbols can be written in terms of two ways. Projective relationship between metric tensors and reconstruction equations. There are two ways. First is by transferring the metric tensor. Second way is to transfer the Christoffel and then writing the metric tensor on surface. And now we have these two. So this is the basic algorithm that we have for each, using by solving these reconstruction normals. So in the infinitesimal planar in terms of Christoffel symbols and the depth by integrating these normals. Compared our method with 5 other methods, 1 and 2, 3 and 5 are the methods that is a method that works on temporal sequences. Amongst these, so this the ground truth and the reconstruction from our art. We measure two kinds of errors here. ES is the of the ground truth and the normals obtained by these is the error between the 3D points. We can see there is a big difference in numbers. Visually, they look very similar. This is because you are now looking from the. If you look at the depth map, you will see difference, and we have very less red regions. Let's have a look at another data set. We see similar things here. We calculate and mean depth error here. And but looking at the depth map, we see these are the following. First, we solve a system of quartics. Second, this is a pointwise solution, so we handle. Third, we definitely need warps between. And last, we outperform the existing work in a